Hi everyone, welcome back. In today's video, we'll look at how to extract the Wirebond inductance and pad capacitance, which are either parasitics or you would like to use them as part of your design for a regular RF Wirebond. So let's get started. The reason I'm starting here and not with HFSS is because I need to show you a few equations and the right circuit model that we need to use. So let's do that quickly and then we'll jump into HFSS. Okay, so that's sort of the title. All right, so the model that we'll use is a pi model, which looks something like this. So you have these admittances between two ports. Okay, so this is port 1, this is port 2, and then you have, like, let's call this the Y admittance of the inductor, admittance of the first capacitor, and admittance of the second capacitor. And then you can show from the Y parameters that you can find the value of these YL, YC1, and YC2 to be equal to minus Y12. YC1 would be Y11 plus Y12, and YC2 would be Y22 plus Y1. So these are fairly easy to show if you know what Y parameters are. You just apply the shorts and opens. For Y parameters, I guess it would be short, right? So when you short out on this side, for example, then this one goes away and you're only left with these two components and so on. So it's fairly easy. I'm not going to do that here. Okay, so once you have this, essentially now what we want to do is to say that, okay, the model that we use looks something like this. It's essentially an inductor with a series resistance of the inductor. So that's what that is. That's the wire bond. And then, of course, you have pads on both sides, right? Either pads or parasitic caps to ground. Model those as two capacitances. And then we have our two ports on either side. It's port 1, this is port 2, because this is some L, R, C1, and C2. And from the equations above, it's fairly easy to show that C1 is nothing but the imaginary part Y11 plus Y12 divided by 2 pi f. C2 is similar, Y22 plus Y12 divided by 2 pi f. And these are coming directly from the definition of admittance of a capacitance and the admittance of an inductor, right? L is imaginary part of minus 1 over Y12 divided by 2 pi f. And R would come out to be the real part of minus 1 over Y12. Right, and the Q of this inductor, since it's omega L over R, the Q is nothing but the imaginary part minus 1 over Y12 divided by the real part. Minus 1 over Y. This is again fairly straightforward to derive. I'm not going to derive them, but these are the results. Okay, so we'll actually use this. So this gives you essentially what all of these parameters are, all the values of the capacitances and inductances directly in terms of the Y, two-port Y parameters, right? Okay, that's fairly good. The thing you need to keep in mind is that this is a circuit model, right? So you need to make sure that the structure you use to extract these inductance and capacitances should faithfully represent this circuit model, and we'll make sure we do that as well. Again, one thing to keep in mind is that the ground is often neglected. So you need to make sure this ground is connected, the grounds of the two ports are connected, and there are no parasitics in the ground path, which can actually happen, and we'll see that, right? So this is an approximate model, of course. It only works up to a certain frequency. Beyond that, you have other effects that come into play. You may have some inductance here, or some resistance on these two branches, some inductance maybe here. There may be some coupling between these two, and so on and so forth, right? But for quote unquote low frequency, this model is fairly accurate, and we'll see how to build a circuit system that has this model. Okay, what are the big advantages of using a pi model rather than other models? Big advantage is that you see that the inductance L is independent of the caps, right? I mean, not the inductance is independent. The inductance is independent of what you connect here, right? Y11 and Y22. So it's independent of these two branches, as you can see here, right? YL is only related to Y12. It's not related to Y11 and Y22. So that's really powerful, which means that the pad capacitances don't affect L very much. Okay, so that's the first thing to keep in mind. YL is independent of C1 and C2. Okay, that's very useful. Second thing to keep in mind is that actually this is not a good model to find the pad capacitances, and we'll see why. C1 and C2 are not stable. Why is that? Okay, we should say not stable as F goes to 0. So at low frequencies, C1 and C2, given this model, are not very stable, and that's because, let me rewrite. Let's just take C1 for example. It's the imaginary part of Y11 plus Y12 over 2 pi F, right? So what happens when F goes to 0? So when F goes to 0, right, in the numerator, Y12, assuming R is 0, Y12 goes to infinity, right? Because it's a wire basically, there's no inductance anymore. And because Y12 starts going to infinity, if you want C to be constant, which of course it is constant, Y11 has to go to negative infinity, right? So that the numerator also goes to 0. And then of course 0 divided by 0, you take the limit, that can converge to a constant, right? Okay, so when you have two terms like this where you have a positive infinity and you want to cancel that with a negative infinity, right? Two large numbers, one positive, one negative, you're dividing that by 0. A small error in either of these, for example, if they don't perfectly cancel out, a small error between these two terms can exponentially grow, right? And you'll see that a small error between Y11 and Y12, which comes from numerical error really when calculating, can blow up this entire term as F goes to 0. That is not the case for L, because for L, when F goes to 0, Y12 goes to infinity, right? And then this whole term goes to 0 directly. There's no plus minus cancellation. And that's why this is a stable expression, right? When F goes to 0, whereas this is not a stable expression. So how do you actually make this stable? So you can make this stable by removing the inductor. Right? If you remove the inductor from this model and you make this an open circuit, then this term goes to 0, right? And then you're left with only this part. And that's like just using the Y parameters of a single one-port network with a cap, right? And we'll do that in simulation, and you'll see that then when F goes to 0, Y11 also goes to 0, and then you get 0 by 0, and that converges very well, right? So that convergence is important to keep in mind. Okay, so that's about that. The third thing that I want to mention is that the model becomes inaccurate at higher frequencies. Yeah, that's fairly obvious to see that other parasitics come into play. And then you also have to keep in mind that if you have some neighboring bonds, they will affect L. So if you have neighboring bonds to the same pad, for example, or two pads that are connected on the other side, on both sides, then it's like two inductances in parallel, and that can reduce the inductance. But more importantly, the mutual inductance between these bonds can matter. Right? And that's something that requires a separate kind of setup and simulation, which I'm not going to do now, but so just keep in mind of the mutual inductance. Okay. And the last thing I should mention is that This model is only to extract L. Okay, it doesn't have to be a faithful representation of the actual circuit that you have. So you just want to extract this inductance, and that's why we are going to build a specific circuit for that. Okay, so we'll see that in simulation. Okay, so with that in mind, we have everything that we need. We know what kind of circuit model we want to use, how to extract the inductance from the Y parameters, and also how to extract the capacitances using a slightly modified version of this. So let's jump into HFSS now and take a look at how to do this. Okay, so what you can do is you can go and download the previous HFSS file that I've used to make the Wirebond simulation that I uploaded earlier. You can find that on my website, so it's right here, RF Wirebond's HFSS design file. You can also watch the tutorial if you haven't already on how to actually draw these wire bonds. I'm not going to go over that again. One thing I should mention is that I also uploaded a document called HFSS Hotkeys and Tips. I'll be using a lot of these during my HFSS videos, and I'm not going to go over it again and again, so you can access them here. It's a nice resource. I'll keep updating this with time. Okay, so let's get into the actual design. So there's one thing that I should mention. Let's actually get started. So let me save this. Then I'm going to copy this model. Okay. All right, so there was one tiny error in the last video's 3D model, which I realized later. It doesn't change the results much, so that's why I'm not going to redo that video. But there was a little bit of a gap, so let's just fix that now. Okay, so there was a gap between the wave port and the ground plane. But since the grounds were all connected, it doesn't matter much. Okay, so now that that's fixed, let's go ahead and change this model a little bit. So I only want to do it for a single wire bond. So what I'm going to do is separate these out, delete these sidelines. I'll delete these wire bonds. And let's get in there. I also want to make this line a standard line rather than a tapered line. And that's because we're going to de-embed the line. So we'll see that if you actually do have a tapered line, you can extract the inductance this way and then go back to the tapered line when you want to extract the capacitances. And we'll do that. Okay, so these are, there's one big port here, right? So we need to make a few changes to the ports as well. Before that, I'm going to delete the perfect boundary on this bottom, and we'll actually make it a upper surface. Let's make it look like copper. Okay. Then I'm going to select this port and move it down. Okay, so that copper is set up there. Okay, yeah, I also need to change the excitations a little bit. So what I'm going to do is I'm going to add integration lines to excitations because we want to make sure that the mode that is solved is in the right polarity, right? You can either have the mode going up or down. And if you don't set this parameter correctly, it will randomly choose which direction the mode is at. Right, and then you say set mode polarity using integration lines, hit OK. It's good, and let's do that for the other port as well. Go from there to there. All right. Okay, so we've added the integration line, deleted the sidelines. Okay, so now if you look at this model, right, let's orient it from the side. Oh, I also want to move these things a bit closer. So I'll select all these faces, edit surface, move faces along vector. Then we'll move it closer just to make the simulation fast. Okay, that's good. So move these guys. Okay, I think that's pretty good. All right, so let's take a look at it from the side. All right. So okay, we have our port here. We have a transmission line coming in. Then we have a wire bond. And of course, there is some pad capacitance down here, right? A wire bond, and then you have another port there with the transmission line to the second port. Now, if you look at this, this is not a good representation of the circuit model that we had, right? So let me actually quickly pull up that circuit model. I'll show you. This is the circuit model that we just made, and you see that we have the caps, we have the inductance and its resistance, but these grounds are connected. Whereas if you go back and look at this model, you see that the one ground is here, and the other ground is up here, and there's some capacitance here, right? So it's almost like circuit model has, you have a cap here, you have a big cap here, a line, another cap, basically two series caps, so one big capacitance between these two grounds, and we want to remove that, right? So let's fix that and see how to fix it correctly as well. So what I'll do to fix it is I'm going to make metal kind of connection between the two. So we'll start from here, say it's XZ, and then I'm going to go all the way maybe down here, and I'll select that face. Hold Z down and then connect them. Okay, so essentially now what I've done is I've connected the grounds. Copper. We make it PEC as well, it doesn't really matter that much. And let's give it the appearance of, okay. So now if you look at this, we have our transmission line coming in, some capacitance here, goes up there, you have some capacitance there, it's connected to the second port, and the grounds are sort of connected this way, right? And we'll see if that's good enough or not. It's actually not good enough. It's close because although the grounds are connected, this big piece of metal has some inductance of its own. Then there is some parasitic cap here, and you also have some inductance here. There's in fact also some capacitance between these two right now, right? So all of this matters a little bit, but we'll try to make it more accurate. So let's just run this simulation. Okay, before that, I also want to change one more thing. Delete this and then create an open region 10 gigahertz. Okay, and we want to change this a little bit. Go from 1 to 30, fine. And we'll set the base simulation at 10 gig. All right. So that's pretty much it, I think. It's always good to check all your layers to make sure that you haven't forgotten to assign something. Okay, looks fine to me. Okay, let's go ahead and simulate this. And while that's simulating, what we can do is we can set up the values. So, okay. So we had the equations for all the different parameters, right? These ones. So that's what I'm going to use. All right. So the imaginary part of y11 is 2 divided by 2 area times the frequency. So that was the capacitance. That's the second capacitance. Minus 1 over by 1, 2 divided by 2 pi f. That's the inductance. And then this divided by imaginary part of this one. sorry, real part. 2, that was the Q, right? Imaginary part over the real part. Okay, in your report. And just 1 divided by this, or not even 1 divided, this was the resistance, right? Okay. Report. Okay, so it's done simulating just in time. Let's change these capacitance numbers. Label C1, C2. This is your L. This is Q. And this is R. Okay, let's take a look at the values. So you can see that the capacitance is kind of unstable, closer and closer to 0. And we'll see actually it becomes more unstable as you change the model. Same one for C2. It's changing quite a lot. Whereas inductance is somewhat stable, right? These are actually not the final values. And the reason behind that is that, once again, we look at the model, right? So in the model, we did not include this big transmission line on this side and this side, right? These transmission lines need to be de-embedded, and that's what we need to do now. So to de-embed, what we'll do is, I'm going to hide these layers. I will measure the distance from here. That's the reason for using waveports as well, is that you can de-embed stuff to here, and that's around 0.69 millimeters on one side. And then on this side, it is measured edge 0.04, right? So port 1 needs to be de-embedded by about 0.69 millimeters. Port 2 by 0.04 millimeters. Okay, and that'll obviously change the S parameter, Y parameters, and you can see now that L has changed. And this is sort of much more stable if you look at the value, right? It's close to 0.96 nanohenry, right? Q, there is some resonance going on here, and that's because the R value went to 0 there, right? So that's not very reliable. The resistance should actually grow with frequency because it's, if you assume inductance is constant, it's omega L. Sorry, so resistance should grow with frequency because of the skin effect, right? And that's why we see that. So what we can do is we can change the scaling on this to 0 to 1,000. Okay, and now we see that it's somewhat more realistic, right? And this model is not really valid beyond, I would say, beyond this point where the resistance starts to drop again. So you can also kind of see the validity of the model in this plot, right? So it's around maybe 12 gigahertz or so. So even the Q is not really valid beyond that, right? And you expect the Q to go up with frequency as long as we have just a constant inductance because it's omega L over R, where omega goes up linearly with frequency and R goes up quadratically with frequency, right? So Q should go up quadratically with frequency. Quadratic, as in, sorry, not quadratic, square root. R goes as a function of square root of F, and L goes as F, so Q should go as square root of F. Okay. So one thing I said is that, is this model really accurate? It's not really that accurate, so we'll change it a little bit and see how things change. So what I'll do is I'm going to take this surface. So you see that we have this kind of big sheet of metal, right? We want to make sure the inductance of this metal is not significant. And that's probably the reason why the inductance here is slightly higher than what it should be. So let's change that. So let's select these two sheets of copper. And ungroup this. Unite these. Okay, I'll actually get rid of, I will make only this part thick first. Okay, So let me go ahead. Sorry. Go ahead and make a big block of metal here. And obviously I need to make sure that touches. Like this. So this is the new piece of metal that we've added, right, to reduce the inductance. I'll unite them. So now it's just a huge chunk of metal, right? Okay. So this should help us improve things a little bit. You can even unite these two. Sorry, unite them. Let's take a look. Okay, so that's like one big chunk of metal now. So let's see how this looks. Let me again simulate this. Okay, now I'll accumulate these plots. So that you can look at a comparison. Once it's done, I'll come back. Okay, simulation is finished. If you take a look, capacitances again are very unstable here and here, whereas the inductance now has dropped. Sorry, the inductance now has dropped, and that's because we've reduced the inductance of that inductor in the ground, right? And it's around like 8.8 or so, and that changes a little based on how much you de-embed this port, right? So for example, we can also de-embed the port completely to this end. That would be 0.75, right? Okay, so if I de-embed by 0.75, oh, sorry, the second port was not de-embedded, my bad. That should change the results quite a bit. Okay, there we go. So the blue line, I think, is when I de-embedded to 0.75, and I see when the gray line, the orange line is when I de-embedded the second port as well. Okay, luckily that port is very close, so it didn't matter that much, but essentially now you see that this is the inductance, right? And it's very stable actually over a very broad bandwidth. But since R is not that accurate because it's very close to zero, and that's the reason that it's sort of fluctuates very rapidly, or it's very sensitive to the circuit model, I should say, not that it fluctuates rapidly, because it's very close to zero, and that's why Q is not very reliable, but it's still good, I would say, up to even 12-15 gigahertz. Okay, let's go back to the inductance. All right, so I removed everything else, and you can see that it's around 8.5 or 0.85 nanohenry for the whole inductance. And there is sort of a rule of thumb that people use to say, okay, what is the actual inductance of a wire bond? And you can kind of approximate it to be around the length of the wire bond in millimeters. So this one is 0.98 or 0.97 millimeters or so. So you expect the inductance to be 0.979 nanohenry, whereas what we are seeing is around 0.85 nanohenry. And that's actually true because that sort of rule of thumb slightly overestimates the inductance. If you use a more empirical model, which is this one, I'll leave a link to the description of this model, where the inductance is given by this equation. So if I put the length to be around 0.979, the diameter is around 1 mil for the inductor, for the wire bond. If we run this, we see that it's around 0.8 nanometer. And you would actually get closer to 0.8, for example, if I also make this piece of metal broad. And you can try that. So that's kind of how you extract the inductance of a wire bond. I still haven't shown you how to do the capacitances of the pads, so let's quickly do that. So all I wanted to show you here is that you have to establish a 3D EM model that is accurate or that faithfully represents the circuit model that you're using to extract these circuit parameters, right? And that's important. It doesn't mean that your chip has to have this big piece of metal here. It just means that this is the closest way to approximate that circuit model. You can obviously use more complicated circuit models and so on, but for a first pass hand calculation, this is very good. You can even rely on this empirical model, I would say. And once you have that, then you can go ahead and design your circuits. And then at the end, you should always check everything with the full 3D model of everything connected, right? Rather than relying on circuit models. Okay, let's quickly do the pad capacitances. So I'll make a copy of this. And let's go in here and simulate this without the Wirebond. Okay, so that's kind of what I talked about in the beginning of the video. Okay, so this simulation is done. If you look at the capacitances now, they're a lot more stable. So C1, which is the parasitic capacitance on line 1, that's really not a capacitor as much because it's just the end of a line. It's sort of fringing fields. And there is also some capacitance to this other side here. So I would say that's not really that relevant. But on this side, it's definitely a huge pad capacitance, right? Because this is, in fact, a parallel plate capacitor out here. So if you look at C2, this is kind of what we see. It's close around 32.5 femtofarads, right? And we can quickly take a look and do a hand calculation just to make sure that those numbers make sense. So if I say, select all these faces and make them visible, let's make the rest invisible. Oh, sorry. Okay, so what I'll do is I'm going to use the area calculator. Go back. Let's just use this. That's around 0.0025 millimeters, right? It's the same for the back. I guess the back has that extra line as well. Okay, so 0.0025, let's use that. And then let's see the separation, top to bottom plate. And that is in Z, is 0.0041, right? Okay, so if I say, okay, capacitance is 0.0025 E minus 6 times silicon dioxide, which is 4 epsilon R, and epsilon naught is something like 8.85 E 17 or minus 17. Epsilon naught value. 12, yeah, sorry, 8.8542 10 to the minus 12. Of course, it has to be negative. Okay, 8.8542 10 to the minus 12 divided by 0.041, was it? 0041, okay. 0041 E minus 3. That gives us around 21.6 femtofarad. Right? And what was the value that we got here? It was around 32. That makes sense, of course, because there's a lot of fringing capacitance to these edges as well. The side, we only calculated this area, whereas the actual area is a little bit bigger than that. So hand calculation makes sense, and also the simulation results make sense. So I think this is sort of reliable, and you can obviously see that C1 and C2 are stable now. They don't go to 0, or they don't go to infinity that rapidly, right? Okay. What else? I think that pretty much covers it. So now you know how to calculate the pad capacitance and Wirebond inductance of a given pad. Of course, if you only care about the pad, then it's fairly straightforward. You just use a one-port network, and then you do this simulation, right? One more thing to keep in mind, I guess, is that when we move this ground all the way till here, we've also introduced some extra capacitance between the line and this ground right here. So, of course, this is like a trade-off between what kind of extraction you want to do and how accurate you want to be in your circuit model and so on. In reality, your ground will be connected through wire bond somewhere else, and that's not what we're going for here. What we're going for here is just how to extract this correctly. So we want to represent the circuit model correctly. I'm not saying, like I said before, I'm not saying that you actually need to connect the grounds like this. Okay, one last thing I should mention before we close is that if you want to accurately find the Q, what you can do is you can set the convergence parameter to be the Q, or even the inductance and capacitance, depending on what you want to find, because HFSS uses the S parameters to converge, but you can use some other parameters as well. So I can set, for example, Y12, right, the real part of Y12 to converge. Add calculation, go to convergence and say use this expression, and you can set the convergence to 1%, and that'll change the results a little bit, but it'll take a longer time to simulate. So that's something to keep in mind when you want more accurate results, right? Okay, so with that, I'd like to kind of conclude here. I'll upload this 3D model as well. I won't upload this 3D model because you already have the previous one. But yeah, hopefully that was useful. If you have any questions or if you find some mistakes that I made, please leave them in the comments below. If not, thank you so much, and I'll see you in the next one.